Hello, our bell ringer today is to indicate the polarity of the bond using a polar arrow and partial charges for a bond between sulfur and nitrogen. If you look at the table with electronegativities in it in your book on page 364, you were able to see that sulfur has an electronegativity of 2.5, while nitrogen has an electronegativity of 3.0. So nitrogen, is the more electronegative, and the arrow will point towards nitrogen, like so. And our partial positive will be over here by the sulfur, and our partial negative will be over here by the nitrogen. Today, we're going to be talking about metallic bonding. And our learning objectives are, I can describe the electron C model, and I can correlate the properties of metals and alloys with the metallic bonding model. We briefly discussed the electron C model several days ago, but the electron C model is how we understand metallic bonding. And the electron C model is kind of comprised of this idea of a delocalized sea of electrons. The metal cores, which is the nucleus and the inner electrons, are arranged in an orderly fashion, and they remain in that orderly fashion because all of those cations, the nucleus and the inner electrons, are attracted to these delocalized electrons that kind of flow through the whole body of all the different cations. We can see this occurring, this sea of electrons phenomena. We can see that with alloys or metals, metal compounds of two or more different types of metals. Let's talk about some of the properties of metals. Metals tend not to be hard or rigid, rather, and if we compare them to ionic solids, that's very, very different. And hopefully you're able to start thinking now as to why the differences between an ionic bonding and a metallic bonding model would lead to those differences. Metals are also very malleable and ductile. Malleable meaning that it can be flattened out into a very thin sheet, and ductile meaning that it can be pulled into a thin wire. And metals are also very good at conducting heat and electricity. All three of these bullet points, so not hard or rigid, malleable and ductile, and conducting heat and electricity, are properties that exist because of the electron C model. So if we look at the picture, for example, on the right, we can see that when we apply some sort of external force, because of the electron C model, because we have these cations that are existing in a structured pattern with electrons flowing freely around them, it's very easy for us to bend or dent any sort of metal rather than break it. Whereas with ionic solids, for example, we saw that applying a force would either cause a very clean split so that those anions and cations wouldn't be near one another, rather than in a metal, where because we have all of the electrons, the negative charge flowing around all of the cations, it's much easier to bend and mold metals. And again, the same is true because, or with the traits of being malleable and ductile, because we can kind of change the shape very easily without disrupting or without incurring any sort of repulsive forces. We can easily mold and manipulate metals, or much more easily than in something like an ionic solid. Also, because again, we've got those free-flowing electrons, we can very easily transfer energy, both in the form of heat, so thermal energy, and in the form of electricity. We have all those free-flowing electrons that are able to move quickly through the metal itself. We tend to see boiling points that are significantly higher than their melting points. And this also has to do, again, with that electron C model. So when we're in the liquid phase, the cations and the electrons are mobile, and they can still balance the charges very easily. However, in order to go to the gas state, we have to disassociate completely the cations from the electrons, and that requires a significant amount of energy. And we see these trends represented very regularly in periods on the periodic table. For example, if you look at group 2A, it has a significantly higher melting point than group 1A. And this is because it has two electrons, two valence electrons that are going to be feeling the stronger attraction to the nucleus, to that positively charged nucleus, more strongly than in group 1A because they only have one electron. So there's going to be a higher metallic character in the group 2A elements than in group 1A, resulting in a higher melting point.